Hello everybody. Today we'll talk about the visual depth perception. You know that we live in 3D and also we move in 3D space, um, and to perceive the depth in the space around us is very important. When you drive or when you walk, you see the distances of different objects around you to find your way. When something is approaching towards you, you need to measure the relative distance, right? To either, save you or protect you, or to, um, grab it. Like when you play baseball, you keep watching the ball approaching towards you, moving towards you, and uh, every moment you are watching the ball, and you then need to move the bat in a space. So to hit the ball, you need to measure the uh, distance of the approaching object, and also you need to measure the distance of your bat and everything, right? So in 3D. So it is extremely important that your visual system can process the depth cues, and your brain actually gets the information about the depth of the static or non-moving as well as moving objects very effectively, uh, and that is very helpful for our movement in the space. So we divide the depth cues into two types. There are several depth cues your brain uses, and we can divide those cues into oculomotor cues and the retinal cues. So oculomotor cues depends on the movement of your eyeball, which is called the convergence, and the movement of the ciliary muscle in the ciliary body of the eye. We already talked about those. So uh, the contraction or relaxation of the ciliary muscle of the ciliary body. And you know that the ciliary muscles contraction and relaxation controls the shape of the lens. So that is called accommodation. So those are the oculomotor clues or cues. Your brain receives those signals from the muscles of the eye, uh, and those are used to determine or detect the uh, distance or depth of the object. Another type of cues are retinal cues or retinal image, the picture that falls on the retina of the eye. Retinal cues are more powerful than the oculomotor cues. You cannot only rely on the oculomotor cues. That's why you need the retinal cues. Those are more powerful to give you the depth perception. Anyway, so oculomotor cues include accommodation and convergence. As I have already mentioned, accommodation is the change of the shape of the lens by the uh, ciliary muscles, and convergence is the movement of the eyeballs in opposite direction. Uh, Retinal cues are divided into monocular and binocular. There are many cues, retinal cues. Um, those cues, give the perception of depth uh, from the single retina. So you don't need both retinas or both eyes to process the monocular cues. So the depth perception can be uh, mm, uh, judged or processed uh, by the brain that goes from a single retina or one side's retina. Uh, and binocular cues include the binocular disparity, which is a very important cue for the fine depth perception. Okay, so the binocular disparity. Yes, the writing is not very good. So binocular disparity is uh, a binocular cue that gives the brain the perception of fine depth discrimination, particularly fine depth perception needs your both eyes. Okay, a relative depth, near or far, relative depth. Okay, so fine depth discrimination and relative uh, depth discrimination um, more depend on the binocular disparity or two retinas. Okay, so here you see that monocular cues and binocular cues, binocular disparity. Now, binocular disparity could be horizontal disparity and vertical disparity. Okay, um, human brain is used to process the horizontal disparity uh, much more than the vertical disparity, because we move in uh, uh, horizontal uh, direction. You know that we walk on the earth horizontally. However, there are creatures like birds, they move up down too, right, in space. So they may depend on vertical disparity a lot too. However, our brain, we don't have many vertical disparity neurons. I studied on monkeys and tried to find some vertical disparity neurons. There are very weak vertical disparity sensitive neurons and very few. I have a published paper on that, but most of the disparity sensitive neurons are horizontal disparity sensitive neurons, and they are pretty strong uh, in terms of processing the horizontal disparity. Okay. Uh, then monocular cues include static and dynamic cues. Static cues, those are non-moving. For example, position-based cues, then size-based cues, and lighting-based cues. Then the position-based cues include occlusion, partial occlusion, and relative size or height. Okay, those are position-based cues. Size-based cues include familiar size, relative size, texture gradient, and linear perspective. Then another cue, static cue, that is the lighting based cues like atmospheric perspective, shading, shadow. Those are the lighting based cues. So you see many cues belong to the monocular cues. You don't need both eyes to perceive the depth by processing these monocular cues. Uh, Binocular cues only includes horizontal and vertical disparity. Now dynamic cues, we already talked about these in last lecture, one of our last lecture, that motion parallax gives us a very good uh, information about the distance. Optic flow, we already talked about that, and another one is deletion and accretion. So this is a nice chart. I really like this one. Very nicely it classified the cues your brain uses, uh, receives from the eye or eyes, one or both eyes, and processes those cues to give you the perception of depth. So you see, so many things are so fast, so quickly processed in the brain, right? Taken to the brain and processed by the brain, because uh, most of the tasks we do, like involved multiple depth information. Accommodation, the ability of the eye to change its focus from distance to near object or in opposite direction from near to far or distance. Uh, and when you move something away from your eyes, like put your a finger in front of your nose and move the finger away from your eyes, the eyes, both eyes move temporal direction, that means laterally, that means in opposite direction, though although both are moving laterally, but they are in opposite direction. You understand that? And um, that is called divergence movement. Okay, uh, and when you move the object closer, then two eyes move to the nasal direction, that means inwards towards each other, that means they are moving in opposite direction. Okay, uh, although they are moving towards each other but opposite direction, and that is called convergence. Now if you move your finger closer and closer, then when it comes pretty close, you see it gets blurry. Why that happens? Because your uh, extraocular muscles or extrinsic eye muscles uh, are now under is getting a lot of pressure on them, and it cannot converge anymore to put the image exactly on the fovea. To see the things clearly, the image must fall on the uh, center part of the retina. You already know that, right? So that's why it gets blurry. So that blurriness is also a good clue for your brain to tell that it is pretty close to your head, right? And if you again move away, gets clear. So you see, two things are here. One is how much movement is occurring in the eyeballs. Uh, uh, the pressure on the extrinsic eye muscles, that is one clue for the brain, and another is blurriness. Now when you move the object away, the pressure on the muscles decreases, okay, gets reduced, less pressure, and the eyes get more like parallel. And if you move the object uh, really, like 1 meter away from the eye, uh, the angle, that is the angle between your two the gazes. Let me draw here. So here see an object and your eyes. So two eyes, right? And so these are eyes. It's the object, the target. Now, uh, if it is far, the object is far, this angle between the line of gazes uh, is less. This is the angle. Okay. Now, if you bring the object closer, then the angle is more, right? Wider. Here, this angle is wider. Wide angle, here narrow, right? So uh, this is when you move this way, the object angle gets larger, and that is convergence, because your eyes move more like, towards each other. So eyes are moving more towards each other, and the pressure on the eye is more. You see the angle is really wide here, uh, very wide angle here, right? So uh, when it comes really very close, like uh, 10 centimeter or less, you can feel your eye muscles working uh, to form the required angle between the lines of gaze. So these lines of gaze, these are the lines of gaze, and the angle between them. Uh, so here the pressure on the muscle is more, on the ocular muscles or extrinsic eye muscles. Pressure is more. So here it will be blurry if it is less than 10 centimeter. And now if you move to like 1 meter away, 1 meter, and then move 10 meter away, if this is the object 10 meter, at 10 meter distance, the eyes are almost parallel, almost no pressure on the muscles. So you see all these, information your brain uh, acquire from the extrinsic eye muscles, and that give good clue of the distance or depth. So this way movement is the convergence, convergence, and taking away the object is divergence type movement of the eye, the opposite. Okay, so that is one thing. That is the vergence that I explained. That is vergence of the eyes. Now, accommodation is different. Accommodation is here. I told you yeah, before that your ciliary muscle in the ciliary body. So this is the ciliary body. And in the ciliary body, you have ciliary muscle, smooth muscle, and from the ciliary muscle here, suspensory ligament uh, also called zonula. The ligaments, same thing. These ligaments uh, go to the lens. So this is the lens, and when the ciliary muscle contraction occurs, you see the shape of the lens changes. When the ciliary muscle, contraction occurs, uh, the lens becomes more round or convex, wider this way. That means the uh, focal distance will be shorter because the lens now will be able to converge the light more, right? So the focus point will be near. If the lens gets flat, then the focal point will be away. That means the focal distance will be further. So this distance is far, this distance is closer. So, and that information that is called, that change is called accommodation. That is the accommodation of the lens, accommodation, um, and that is done by the ciliary muscle, right? So from the ciliary muscles, information also goes to the brain. You know that when you move again, you put your finger in front of your nose, and if you move it away, right, it gets smaller in size because the image on the retina uh, gets smaller. That's why, although the actual size is not changing, but you see it is getting smaller, right, as you move away. So that is also a good clue for your brain to uh, give you the relative distance, okay, of the object. Particularly the moving object, you can tell that it's getting smaller as it goes away, and your shape of your lens is also changing. When you bring closer, the lens gets more round, right? Due to the contraction of the ciliary muscle. As you take away, lens gets less round. Okay, and those changes occur due to accommodation. And the goal, already, we talked about that a lot before. The goal is putting the focus exactly on the retina, right? That's why the shape of the lens changes um, to put the focus or focusing the uh, image exactly on the retina, to the center of the retina. Okay, so we already talked about the Vergence last slide. We already talked about Vergence. You see the angle changes, right? Here, in this case, you see the angle. It says 33 degree. The object is only 10 centimeter away, so a lot of pressure on the ocular muscles. Here, if you move it to 1 meter away from the eyes, less pressure on the muscle, and the angle here is only 3.5 degree. And this is 4 meter or more from the eye. The angle is less than 1 degree, less than 1 degree angle. Okay, so here the eyes are parallel or almost parallel. Uh, Whatever the spelling, parallel here. Okay, okay. So now let's see what we are going to do next. So those two are the cues, very important cues. Those are oculomotor cues. Okay, accommodation and convergence. Now let's move to the retinal cues. Retinal cues. One important retinal cue is familiar size. You know that these palm trees are uh, same sized. Okay, we know that these are just think that these two are same sized tree. And now this one is near to your eyes, so you see the picture that falls on the retina is from the red lines going to the retina is much larger here. This is the size of the picture on the retina, two red lines here, right? And as you move it away, or you see another tree, same sized tree, uh, which is double distance. This is half, this is double. So this is the distance, and this is the double distance of that 2D. And now from this one, since the size, as since the size on the retina here is half of this one, that's why you see this one much smaller. You see the blue lines here, the distance, red lines double. So the picture falls on the retina from the distance, double distance one is half sized than this one, and that's why you see this one smaller and this one larger, because your brain gets signal from the retina, right? Not from outside, from the retina. So whatever the retina sends to your brain will process that, right? So that's why your brain sees the far things smaller, near things larger, although they are same sized. Same sized. Makes sense? uh, and we know a lot of things from our experience, and that helps a lot to give you the perception of distance or depth. For example, this is a golf ball, this is a basketball, and this is this is a baseball, and this is a basketball. Okay, so now we all know that golf ball is much smaller than the baseball, and baseball is much smaller than the basketball. Okay, now if on your retina the picture uh, of all those three balls, the size of the picture is same, then your brain will, since your brain knows that this picture is a basketball picture, this is a baseball picture, and this is a golf picture ball, because we know by looking at the color or shape that which ball is that. So although the brain in this case receives the same size from the retina, because on the retina the size is same, uh, the brain will know that uh, this one basketball is farther away, much farther than the baseball, and baseball is much farther than the golf ball, and that's why the size of those three are same on the retina. Brain will know that, because from our experience we know that if they are in same distance, then the size of the image on the retina from the golf will be much smaller than the size of the baseball, and the size of the basketball of the on the retina will be much bigger than other two, right? If they are at the same distance, then this one on the retina will be bigger than this one, and this one will be bigger than this one. So since they are same, that means they are in three different distances. So that's how the familiar size of the things also play important role to give you the depth perception. So again, relative size, we every day in our life we measure or depend on this strong retinal image cue a lot, right? That different things are at different distances, and we know that these cars are same sized or almost same sized, but this is much smaller. Why? Because the distance is further. Uh, Other cues also help together. You see here only not only relative size, but there are other cues around. We'll talk about those. Okay, so all these cues, multiple cues, are here. So we actually talked about the retinal image size and how it can be changed and give you or your brain the clues of the distance or depth. Relative size, this is another interesting, very commonly used picture. You see, we know that two people, they are almost same sized human being. Uh, However, this one doesn't look any odd, like it is not odd. This one looks very odd. It's very odd. Why? Because this is unfamiliar. We don't think that this makes sense, but this makes sense, and this is usual. So you see, we can get very clear idea that this person is further away than this one. This one doesn't give any sense unless that person is really very small. But again, we don't depend on only one cue. You see, the size of the chair cannot is also smaller, and uh, a lot of things. This is not very clear, blurry. This is very clear. We know near objects are clear. As you look far, gets less clear. Yeah, although too near is again blurry. Interposition, partial occlusion, another retinal image cue. Uh, you see that this one you don't see completely because part of it is covered by the blue one. So red one is partially covered by the blue one. So you definitely think that this red one, the shape of, although you don't see, your visual system used to see this, and you will think that your eye or brain will think that this is actually a complete thing here. Okay, and this is also complete. So two round things are there, and since you don't see it completely, that means this one is behind, right? And this one is in the front. So that is the partial occlusion, okay, or interposition. Uh, we use that clue or cue a lot, right? For example, here you see that definitely will tell that this girl is near, uh, and the car, since it is partially occluded or blocked, uh, that is far, right? So there are many objects here in this scene. So this is a visual scene where you have multiple objects, and they are differently occluded or uh, blocked by different things. So linear perspective. This is another retinal cue, image cue. You see, we know that as you look further, the things converge, get narrow. Like if you see two train lines here, if you see the far, and this is near, you see, as the lines go farther, they converge, they come close to each other. So, although they are in same distance from each other, this is usual picture, right? So that means that this is far end, this is near end. Same thing here. You see the platform of this station, and this is the roof of the station. So you see they are getting near vertically. This is horizontally, this is vertically. So from all directions you see the things um, get closer as you look further. Okay, so this is another very powerful uh, retinal cue, that is the linear perspective. And all these are monocular cues. You don't need two eyes or two retinas. Monocular cues. Just close your one eye, still you can see the same and perceive same. If you go back to previous ones, all these are monocular, like you can tell with one eye. So these are all monocular cues. This is another monocular cue, and we know that near things here, if you see near part of the mountain, it is pretty clear, and the color is more bright. And if you look the far mountain here, you see the blurriness, and the color gets dull and blurry. So that is one thing your brain uses. Far mountain or far things get blurry because the light comes from the far things, far objects, uh, travel a lot, right? But from the near objects, the light travels less to your eyes. So when the light travels from the far objects uh, in the atmosphere, scattering of the light occurs more. That makes sense, right? In the air or atmosphere. So when it arrives into your eyes, it's already, uh, a lot of scattering has occurred, and that's why you see the blurriness. Okay. Uh, Another thing, if you see the distant object, for example, if you look upwards, you see the sky or see the far mountain, it looks bluish than the near. Why you see the sky is blue or far mountains are blue, although blurry, far mountain, but bluish. The reason is the scattering of the shortest length lights. You know that blue lights are the length of blue light is short, okay, and they can scatter more. So you can see the bluish sky is blue. If uh, you didn't have that, the blue lights, distance mountains appear blue. Uh, if you didn't see the sky is blue, then you would have seen the dark in the space. So you would have seen the space, and which is very dark. Like if you go to the moon and see uh, the space from the moon, it looks dark because no cloud is there, no blockage of the blue lights uh, occur. Shadowing. Shadowing is an important clue, and this one, all these clues are also called, not only they are called monocular cues or retinal cues, they are also called pictorial cues. So they are used in pictures or paintings a lot, and the painters use all these cues to give you the perception of different depths in 2D surface on 2D surface or 2D picture. And light and shade, these are used a lot in paintings. You know that. Uh, we know that we are getting the light from the sun above, from above the earth. So we are experienced or used to that, right? This light comes from above. So that means what? The objects are getting the light first, will be bright, right? So the objects are uh, upwards, more outwards, they will get the light first, and the objects are like in the deeper part will get less light. So how much light is being falling on the object, and how much light is not falling on the object, that gives you the perception of depth. For example, in these balls, you see the top part is brighter and the bottom part is dark. That means that we can tell that light is coming from this way. Make sense? And this object, although on 2D, but now your brain is perceiving that this part is first getting the light. So light is coming from this way, and this whole thing is like elevated. That's why it is, getting the light in this part. And since it is elevated, this part, back part, is not getting the light. Okay, so that gives you a perception that it is pushed out, or it's like an elevated object. Opposite is here. You see that if you uh, think this is a deep uh, object like a ball, uh, and light is coming from this way, okay, and if the light is coming from this way, uh, the wall, this wall will block the light, so this part will be dark. However, light will reach here more. So just inside the wall, the inner side of the wall, this side will have less light, this side will have more light. So that gives you the perception of a deep object, or uh, well, or something like it's a concave thing. Here, same strategy has been used, light and shade. So light, bright areas are elevated areas, and less light areas are uh, uh, deeper areas. So you see that very strong uh, sense of 3D or depth, elevation or depression is given by the light. And the experience, how your brain is experienced to see the light in on the earth. Okay, so all those I talked about are monocular, retinal, pictorial cues, and static. Now you know that there are three cues. Those are motion cues. So those are dynamic or motion cues. Motion or dynamic cues. Motion parallax, optic flow, and deletion and accretion. We already talked about motion parallax and optic flow. you will see the we already also talked about occlusion of static things. Now you see uh, deletion and accretion. So if you see a person is walking, so you see his whole body movement, and then if that person is first partially blocked, then completely blocked here, and then partially blocked, and then appeared fully here. So that moving subject is being blocked by this object, right? So starting partially, then complete, then partial appearance, and then full appearance. So this is the deletion, blockage, and then this is accretion. So those two things together uh, gives you the perception that the person walked, moved, and passed through that object, right? So uh, that is another cue, but these cues are uh, motion cues or dynamic cues. So three dynamic cues. This is one, and optic flow. You already know when you move forward, the objects get expanded or larger. That means you feel that they are moving towards you, and that motion, uh, apparent motion, gives you the perception that you are moving forward. And if you move rightwards, the things optic flow, the things move left, and that gives you the perception. Now if you are static and you can create those motions in space, like the things are moving to all those things are moving towards you in the space, then you feel that you are moving fast. If they move towards you very fast, you move that you are moving forward very fast. If they get slow, then you feel that you are getting slow. So virtual reality shows this optic flow is used a lot. You are sitting in a chair, and the things around you are you know moving, not real motion. Um, and that gives you the perception that you are moving in all different directions, right? So that is the optic flow. Uh, then another is the motion parallax. We also talked about that. Motion parallax is another clue uh, that your visual system uses when you move, like you are driving a car this way. You see the lampposts or the trees near you pretty fast move in opposite direction. However, if you see the distant mountain or trees or bush, you see that the things are moving like this slowly. This one is fast. These objects move very fast, near objects, and far objects move slow. And the direction is also an opposite direction. So you feel that whole picture outside of the car is moving like in a rotation. Uh, so that is the motion parallax. Very important cue. For this one, you definitely, for optic flow, to create strong optic flow depth perception, you need large visual field, right? In a small visual field, in a small aperture, you won't feel any motion even if you move the you create the optic flow in a small circle in front of you. It will not give you any clue, but you must sit in a very big large field, and that's why we say that MST MSTD, neurons have very large receptive field, so they are probably more useful to process the motion from optic flow. Um, Motion parallax also, needs MSTD neuron, but few experiments have shown that MT can also be, you know, uh, receiving uh, the optic motion parallax information or processing motion parallax information. So this is the way we do experiment. We did actually. I was involved in that too. You let the monkey sit on the monkey chair, or the subject sit on the chair, and in front of the subject on big screen, you ask the subject to fixate here, fixation point, and you can create the motion parallax stimulus in front of that subject uh, by moving the near things. When you uh, move right or left, your near thing moves to opposite direction. You can just test that. Put your two fingers into different distances, and now you move your head right and left. You can see that near finger is moving to opposite direction of your head movement, and faster, and far thing is moving uh, to same direction but slower, less movement. So this one will move towards your head movement. If your head moves this way, this will also move this way, but the amount will be less, and this one will move the other way and faster. Okay, so that is the motion parallax. Optic flow, we already talked about that. Now, uh, binocular disparity is the binocular cue. This is the only binocular cue, and as I told you, it could be horizontal, and your brain processes horizontal cue better than vertical, because we walk on the surface of the earth uh, horizontally. So most of the neurons we record are sensitive to horizontal binocular disparity. Now, what is the disparity? If you put your finger in front of your nose and move, close and open your right and left eyes, you can test it. You put your finger in front of your head and move, close and open your right and left eyes, you see the object also moves right and left slightly. Why is that? Just think that your two eyes are two separate cameras, okay, slightly apart horizontally. We know that your eyes are apart or separated horizontally, and now these are two separate cameras, right? And this is the object. So now uh, if you take picture by this camera, the image will be little bit different than the picture you take by this camera. If you do this, you'll see when you will put these pictures side by side, you'll see they are slightly, you know, uh, most part is overlapping, but slightly uh, apart from each other. So that is exactly what your two eyes are doing. They are placed away from each other horizontally, and that's why when you see the object with your right eye and then left eye alternatively, you see the object is in slightly different locations horizontally, and your brain um, takes that information from your retinas, that how much you know uh, non-overlapping is there, and that is a very strong cue for your brain, and that is called the binocular disparity. So your right and left eyes see the things in space in slightly different locations in space, and that is the binocular disparity. Your brain uses that as a clue. Binocular disparity is used, as I mentioned before, for fine depth and relative distance or depth. Okay, and horizontally placed eyed creatures use binocular disparity mostly because their eyes are horizontally and they move horizontally on the earth surface of the earth. Horopter, the term horopter is the plane. You see the dotted line here. This is the horopter. When the object is anywhere on this plane and you fixate your eyes on that, that is called zero disparity or uncrossed zero disparity, same depth or distance. Okay, the distance will be perceived same, and that is horopter. Now so the definition of horopter, you can say that an imaginary surface defined by the locations in a space from which the objects would project retinal images at corresponding points. Okay, so fully overlapped. There is no unoverlapped part. So that's the zero disparity and same depth in all these locations. Anywhere on the horopter, the distance or depth will be same. Now this object is on the horopter line. So this is the, if you fixate your eyes here, that's the zero disparity, right? Now if you see another object closer than this fixation point, then what will happen? Let's first talk about this one. This is zero disparity, means the picture from this object falls on the retina on exactly the same location. That means on the fovea of right retina fovea and left retinal fovea. So uh, exactly they are superimposed to each other, and both are on the fovea. Why? Because you know that your eyes are fixated on this one, right? So you're looking exactly on this point or this object, so the picture will fall on the fovea of the retina of right and left. So no, you know, displacement between these two. Now while you are fixating, now if you bring the object near, or if you look an object closer than the, you know, horopter, then what will happen, you see that from the this object the picture on the retina will fall here and here, the green object. And now if you bring much closer here, the brown one, the picture on right and left retina will be here and here. Okay, so the fovea is this one, red one, right? So fovea is here, and green one is slightly lateral to the fovea. So this is the distance from the fovea here. And then if you look at this one very near, then the picture on the fovea here and here. Okay. So now the angle, we talked about that before. Uh, all these are called cross disparity. So anything near than the fixation point, those are crossed disparity. Uh, why we say crossed? Because as you move the object near, you have to move your eyes towards each other. That means that's the convergence. Okay, so crossed disparity uh, occurs in convergence. Okay, convergence. So near than the horopter. Now these objects you see are further away, far objects. Your fixation is here. Now you are paying attention to the further object. So uh, in this case, you see the pictures fall medially, medial to the fixation point. This is the fixation point here. Okay, so the pictures are in the nasal side. Same thing here. This is the fixation point for this one, and as you move the objects far, the retinal uh, images are placed towards the nasal side. Near, the retinal images are placed towards the temporal side, okay, of the fovea. So in this cases, uh, retinal, this is the fovea here, retinal images laterally, temporal side. In these cases, objects are near, that means this is the fovea, the images on the nasal side are medially. So this is called the uncrossed disparity. Okay, but here you see all are uncrossed. This is uncrossed, this is uncrossed because both are away further, but this one is less uncrossed, this one is more uncrossed. Smaller uncrossed disparity, larger uncrossed disparity, the red one. And same thing here, larger crossed and smaller crossed disparity. So those are the crossed and uncrossed um, disparity. Corresponding points, a point on the left retina and a point on the right retina that would coincide, that I mentioned already, if the two retinas were superimposed. So if you superimpose right and left retina, put one on another, if they are just exactly covering each other or superimpose each other, that is the corresponding point. For example, foveas of two eyes, when the picture falls exactly on the foveas of your right and left eyes, that is the corresponding uh, points when you fixate your eyes in front of your head. non-corresponding point, a point on the left retina and a point on the right retina that won't coincide if the two retinas are superimposed. Okay, we talked about horopter, always on the corresponding point in case of horopter. Crossed, uncrossed disparity, we have already talked about those. Okay, now the last thing you already know that inside the MT you have direction as well as disparity sensitive neurons, right? You must remember the patches I showed you, like far, near, far. So these neurons responds to far. Far means far than the fixation point or horopter. So these neurons responds to near. So far disparity is indicated by plus, near disparity indicated by minus. So negative disparity indicates that the object is near than the fixation point, and positive disparity is the uncrossed disparity further. And you see that how these neurons, disparity sensitive neurons, respond. Disparity sensitive neurons. So different neurons respond to different disparity. So different neurons are sensitive to different disparity. We know already that some neurons are sensitive to far, that means positive disparity. Some neurons are sensitive to near, that means negative disparity. However, the positive could be many different distances, right? Far could be, near or far. Near could be near or far. So that's why you have the map, very nice map, and the neurons respond to, like, all these are near neurons. Okay, this is the fixation point. The neuron responds to zero disparity. Okay, so this is zero disparity fixation point, fixation, and this is your eye. Okay, and these are the neurons, like far, plus, minus, near. So the near could be, different minus values. This one is not too near, but this one is very near, right? So if this is point minus 0.1 disparity, for example, this is minus 2.0, and all these are in between. Very systematic way it goes towards more negative. And same thing here, this is like 0.1 positive, and this is 2 positive, 2.0. So these neurons are gradually getting larger disparity. So that's why you have systematic map in these patches in the MT, and different neurons responds to different disparity. And this is one neuron. You see here, this is the fixation point. So you have fixated your eyes on this cactus, and then you are looking, while you are fixating here, you are looking something here. Okay, and from this one, the picture falls here, and from fixation on the fovea, right? So the distance here, you see, from the fovea and from the picture of this cactus, this is on the fovea, this is outside of the fovea. The distance on the retina, this distance, this neuron doesn't like, but some other neurons would like that. This is another neuron you have recorded. You have moved the object away, but still this neuron doesn't like that. Okay, so no signal. However, if you move it near than the fixation point, since this neuron is a near neuron minus, it likes near object. So now this neuron would respond. You see the response here. Action potential or firing has increased. So that means this neuron likes near, not only near, how much near? That is the distance. So some neurons will like not will all the near neuron will not like this one. Probably the object should be here to excite that neuron. Make sense? For neurons, some neurons probably will be excited if you move the object here. Some neuron will be excited object here. So for neurons. So that's how a retinal image goes to the brain, and the brain, the neurons get excited. That particular group of neurons, and then your brain collects that information and gives you the perception that which groups of neurons are being excited, and that tells the brain that where the object is. So that is how the disparity sensitive neurons work. Okay, so let's stop here. These are the things you need to know about the visual depth perception. Thank you.